In video 6, we talked about hash-based sharding, applying a hash function to a shard key to decide which database node stores a piece of data. But there's a serious problem with naive hashing at scale. What happens when you need to add a node because traffic grows, or remove a node because it failed? With naive hashing, almost all your data needs to move. In a system with millions of items and dozens of nodes, that's a catastrophe. Consistent hashing solves this problem elegantly. It's used by Cassandra, DynamoDB, Akamai's CDN, and almost every large-scale distributed storage system. Understanding it will make you stand out in system design interviews. Naive hashing works like this. You have n nodes. For each key, you compute hash key mod n to find which node it belongs to. Simple, uniform distribution. Works perfectly until n changes. When you add a node, n becomes n plus 1. Now hash key mod n plus in 1 gives completely different results for almost every key. The data that was on node 3 now belongs on node 7. The data on node 1 now belongs on node 4. Virtually every piece of data needs to move to its new node. In a real system, this is tens of millions of database records migrating all at once. Catastrophic. Here's a concrete way to feel the scale of the problem. You have 4 nodes and 1 million keys. You add a single node, now you have 5. With mod 4, the key user 12345 hash to node 2. With mod 5, it might hash to node 4. That's not just one key affected. Statistically, about 80% of all your keys map to a different node when n changes by even 1. So adding one node triggers the movement of 800,000 records. In a database cluster, those are network transfers happening simultaneously, saturating bandwidth, causing latency spikes, and potentially causing cascading failures. This is not a theoretical concern. In 2014, an AWS Elasticache cluster restart triggered a data reshuffling event that took down a customer's service for over an hour because their sharding was modulo-based, and the cache needed to repopulate from scratch. Consistent hashing solves this with a simple but brilliant idea. Arrange nodes on a ring. Imagine a circular number line from 0 to 2032. 1. Hash each node to a position on this ring. Then hash each key to a position on the ring and assign it to the first node you encounter when moving clockwise. Here's why it's elegant. When you add a new node, it takes only the keys that were going to the next node clockwise. All other keys stay exactly where they are. When you remove a node, its keys go to the next node clockwise. All other keys are unaffected. In a system with n nodes and k keys, adding or removing one node remaps only kn keys, not all k of them. Compare that to modulo hashing. If you have 4 nodes and 1 million keys, adding a node remaps 800,000 keys. With consistent hashing and 4 nodes, adding a node remaps 250,000 keys, exactly 1 to 4 of them. Add more nodes and the fraction per node change gets smaller. At 100 nodes, only 10,000 keys move on a node change, 1% of your key space. This is the mathematical guarantee that makes consistent hashing practical at scale. The lookup process works as follows. You have a hash function that takes a node name or IP address and produces a 32-bit integer, its position on the ring. You do the same for every key. To find which node owns a key, you compute the key's hash, then scan clockwise on the ring until you hit a node, typically implemented with a sorted data structure, a sorted array, or a tree, so the clockwise lookup is O log n. There's a catch. With only a few physical nodes on the ring, the key distribution is uneven. By chance, some nodes might end up responsible for 40% of the key space, while others cover only 5%. A node failure could then overload the next node with all of that failed node's traffic, creating a cascade. The solution is virtual nodes. With virtual nodes, each physical server is placed at, say, 150 positions around the ring instead of one. These 150 positions are spread uniformly around the ring. Now, each physical node owns many small key ranges distributed across the ring, rather than one large contiguous range. The average owned key range across all nodes becomes very similar. When you add a new physical node, it claims some virtual nodes from existing nodes. Load distributes gradually across many donors, rather than one node suddenly giving up half its data. Cassandra uses 256 virtual nodes per physical node by default. So a 10-node Cassandra cluster has 2,560 virtual node positions on the ring. When you add an 11th physical node, it distributes its 256 virtual positions across the ring. Each existing node gives up roughly 23 virtual nodes. The load transfer is smooth and proportional across all 10 existing nodes, rather than one node suddenly shedding half its data. The trade-off with virtual nodes is memory overhead for the routing table. With 256 vnodes per server and 100 servers, you have 25,600 entries in your ring data structure. This is manageable, typically a few megabytes, but it's worth being aware of. Consistent hashing appears in several contexts you'll need to discuss in system design interviews. In distributed caches like memcached, consistent hashing determines which cache server holds each key. When a cache server is added during a traffic spike, only 1N of cache keys need to be warmed, not all of them. In distributed databases like Cassandra and DynamoDB, consistent hashing determines which node is responsible for each partition of data. In content delivery networks, consistent hashing maps requests to edge servers. Akamai's CDN uses a variant of consistent hashing to route billions of requests per day. Amazon's Dynamo paper from 2007 is the seminal reference here. Dynamo introduced the combination of consistent hashing, virtual nodes, and vector clocks that became the blueprint for a generation of distributed databases. DynamoDB, Cassandra, and Riak all descend directly from those ideas. In a Cassandra cluster, when a write arrives, the coordinator node computes the hash of the partition key and uses the ring to identify which node is the primary replica. Then, based on the replication factor, it identifies the next clockwise nodes as additional replica targets. The write is sent to all replica nodes simultaneously using a quorum write, typically requiring acknowledgement from a majority before confirming success to the client. This is important to understand in interviews. Consistent hashing in production systems is almost never used alone. It's always combined with replication and a consistency model, quorum reads, writes, eventual consistency, or tunable consistency, as in Cassandra. Consistent hashing also cleanly handles replication. The primary node for a key is the first node clockwise, but you can replicate to the next N1 nodes clockwise as well. Cassandra calls this the replication factor. A replication factor of 3 means every key is stored on 3 consecutive nodes on the ring. If one fails, the data is still available on the other 2. The replication factor interacts with your quorum settings. In Cassandra, you configure reads and writes to require acknowledgement from a quorum of replicas, typically a majority. With RF3, a quorum is 2. So a write completes when 2 of 3 replica nodes confirm. A read succeeds when 2 of 3 nodes respond. As long as the read quorum and write quorum together exceed the replication factor, read plus write RF, you're guaranteed to see the latest write on every read. This is why RF3 with quorum reads and writes is the standard production configuration. It tolerates a single node failure on either reads or writes without sacrificing consistency. Here is the precise language to use when consistent hashing comes up in interviews. This applies whether you are designing a distributed database, a distributed cache, or a CDN. The moment you have data distributed across multiple nodes and the number of nodes can change, consistent hashing is the right answer for routing. Say it unprompted. Don't wait for the interviewer to ask about it. Use this structure. First, state the problem. Naive modulo hashing causes massive data movement on node changes. With n nodes and k keys, modulo hashing remaps approximately k, 1, n plus 1 keys when a node is added, effectively all of them at large scale. Second, state the solution. Consistent hashing maps both nodes and keys to a hash ring. On a node addition, only key n keys need to be remapped, exactly the 1n fraction previously owned by the next clockwise node. Third, add virtual nodes. To avoid uneven distribution from random node placement, use virtual nodes. Cassandra uses 256 virtual nodes per physical node. This distributes load evenly and makes adding nodes smooth across many donors. Fourth, add replication. The first node clockwise is the primary. Replicate to the next RF1 nodes clockwise. RF3 is standard. Anytime you design a system with a distributed cache cluster, a distributed key value store, or CDN edge server selection, this is the answer. Mention it before the interviewer asks. A few concrete numbers that anchor consistent hashing in interviews. With n nodes and k keys, a node addition or removal remaps exactly kn keys under consistent hashing. Compare to modulo hashing, which remaps approximately 80% of keys when n changes by 1, regardless of the size of n. Cassandra uses 256 virtual nodes per physical node by default. A 20-node cluster has 5,120 virtual node positions on the ring. Adding a 21st node claims 256 of those positions, about 5%, spread evenly across all 20 existing nodes. A Cassandra cluster with RF3 tolerates the loss of any single node without data loss or read unavailability, assuming quorum reads are configured. DynamoDB uses consistent hashing internally but exposes it differently. Partitions are managed automatically and opaque to the user. The underlying principle is identical. Akamai routes roughly 30% of global web traffic through a CDN architecture that originated from consistent hashing research published in 1997 by David Karger at MIT, the paper that coined the term. In a typical production distributed cache configuration, 10 nodes, 256 virtual nodes each, RF1, caches are not replicated. A cache miss just means a database read. Adding one node remaps 10% of cache keys, causing a temporary increase in cache misses. This is expected and acceptable. Plan for it in capacity. Consistent hashing is the mechanism that makes distributed data routing work without catastrophic reshuffling. You now understand the problem it solves, how the ring works, why virtual nodes exist, and how replication factor fits in. You have the numbers to back it up in an interview. In the next video, we move to one of the most architecturally important patterns in large-scale systems, message queues and event streaming. This is the technology behind Uber's real-time dispatch, Twitter's notification system, and every large-scale async workflow you'll encounter in a system design interview. We'll cover RabbitMQ, Kafka, delivery semantics, and precisely when to use each. See you in video 9.